Usually I will then repost them with a little thing that says slides edited such and such a day. Generally it will just be adding in a slide here or there. Okay, so this is chapter 16. There are some things you need to know going into this chapter. This is 1C. This means that we expect you to know all the things we taught you in 1A and 1B, right? Chemistry does not exist in a vacuum of the rest of the knowledge. So it's not like you have now entered into 1C, forget everything from A and B. That's definitely not true. This builds on everything from A and B. So you definitely need to know your naming. This gets skipped over a little bit in 1A sometimes because we also sort of expect you to know this from high school, and so sometimes it doesn't always get taught a huge amount. If you didn't learn it there, learn it now. And you're welcome to come to office hours and ask for help on any of this stuff too. Again, don't think of office hours as, oh, well, she says I should already know this and I don't. I'm not going to go admit that I don't know something to her. No, that's what I'm here for. Admit that you don't know things and I will help you. You need to know how to balance reactions. You need to know basic stoichiometry. By basic stoichiometry here, I don't mean easy stoichiometry. I mean stoichiometry in the sense of, hey, this is the stuff that we taught you in 1A and 1B. And then all your gas law materials. So I think this ends up being chapters 5, 8, and 11 in your book. If you don't know that, you're going to be in a little bit of trouble. We will do some things with thermodynamics as well. So some of that you need to know as well. Most of that's pretty fresh in your mind though, because you just came from 1B. This is the stuff I was more concerned about maybe got forgotten over the last quarter. Okay, everything that we learn in this chapter is going to be built on in the next 2. So spend a lot of time on this chapter, because if you get behind now, you're going to have a lot of trouble with acid-base chemistry and with ionic aqueous equilibria. So what happens is we learn the basics of equilibria here, and then we say, okay, this is great, but there's these specific cases called acids and bases. Let's figure out how we do it there. But it's basically the exact same thing, just in a new application with some new terminology, some new definitions. Once we get that, then we just kind of build on that when we go into aqueous equilibria. So this chapter is really, really important to get. So important that we actually shifted things around just so that we would start off 1C with this chapter, so that you would have it. This slide is mostly for you. These will be in the front of each chapter. These are things that by the time you get to the exam that you should be able to do. You should be able to use this as a checklist where you can go through and say, oh yeah, I can do that forwards, backwards, and in a new application for each one. And we'll have short versions of these for each section too. Okay, first things first, dynamic equilibrium. We need to know what this is. So we have this escalator, it's a little glitchy, but you see the escalator coming down, you see the guy walking up. They're both moving. The escalator is moving down, the guy is moving up, and yet is he going anywhere? No, he's stuck, right? That's what a dynamic equilibrium is. Things are happening, things are going back and forth, and yet nothing is really changing. So we want to first define dynamic equilibrium, and then for this little section here, we want to make sure that when we're given a time course graph, so a graph of what's going on during the reaction, that we can figure out exactly when equilibrium hits. And once we see the graph, we'll see how that works. So I like the escalator example, but there's a few other analogies we can use. So all of the analogies that I use in this class, I tend to like analogies, mostly because students tend to like analogies. If you're someone who hates them, just don't pay attention to it, it's fine. I will never give you a test question on, so that one time when I was talking about throwing balls back and forth, it's not gonna happen. Okay, so we have me and my friends against the Avengers. Kind of a theme here going today. All right, so we can take a guess here who's going to generally win this contest, right? Well, so we start off by giving me and my team 10,000 balls to throw. The Avengers don't get any. And the goal is that we're going to throw back and forth, back and forth, back and forth and see what happens. So they initially have 0, we initially have 10,000, and we start going. Now, notice we can't actually set up an equilibrium right away, right? Because right away, the Avengers can't throw anything back because they don't have any to begin with. So we have to throw that to them before they can start throwing it back. What happens when we say equilibrium is reached? We mean that the number of things going back and forth doesn't change. we're still going to be throwing them back and forth. Me and my teammates are going to be trying really, really hard, and they're just going to keep tossing them back at us. But we're going to actually be throwing them back and forth until we end the simulation, because mine and my team has passed out. So we get done with this, and a lot has changed, right? Instead of 10,000, we now have 9,997, because every time we throw them at the Avengers, they throw them right back to us really quickly. So they end up with 3, basically, because it takes a half second to throw it. Okay. So why talk through this? Well, there's some really important similarities here to actual chemical equilibrium and how you want to think about chemical equilibrium before we start talking about the numbers. So first off, once we reach this point, we can wait 10 minutes and it's still going to be the same. They're still going to have about 3, and we're still going to have about 9,997. And yet we're still throwing them back and forth. This is exactly how forward and reverse reactions work. The forward reaction is proceeding, the reverse reaction is proceeding, and yet they're proceeding at the same speed, right? So when I throw 3 balls to the Avengers, they throw 3 back. When I throw 3 to them, they throw 3 back. It's back and forth at the same speed. Now, you guys got to do kinetics already, which is nice. That was another rearrangement we did. So this is actually the reason why the kinetics, why the rates are based on concentration. We can see that here. If the Avengers had a bunch more balls, the equilibrium would change, right? And we'd have to reestablish equilibrium. And keep that in mind too. Okay, so now let's talk about this in terms of chemicals. So there's actually 2 different kinds of equilibrium. We're gonna just basically be focused on the bottom one, but we should mention the top one a little bit. So we have equilibrium when it comes to physical equilibrium. So if we have water molecules in a closed off beaker so they can't escape, we'll have water vapor, right? You learned about that in 1B, kind of talked about it a little bit in 1A, not a lot, but mostly in 1B. And what this allows us to do is say, okay, well, these water molecules are evaporating, but at the same time, these water molecules are condensing. So we have an equilibrium set up. Nothing actually changes in the terms of numbers. The numbers of evaporated or gas molecules is going to be the same at time 2 minutes as it is at time 2 minutes 30 seconds, and yet they're continually going back and forth, okay? Mostly we're going to spend our time here on chemical equilibrium. So here we have an actual reaction happening. We'll have a few example problems with this particular reaction too. And we have the forward reaction, we have the reverse reaction. They're both happening simultaneously. So it's going forward and it's going backward, and they're going forward and backward eventually once equilibrium is reached at the exact same speed, okay? So there's a set of circumstances for these, not all reactions do this, but for the ones that do it, where the forward and the reverse reaction are going to be happening at the same rate. And when that happens, we have a dynamic equilibrium. Now, notice I keep saying once equilibrium is reached. If you just toss a bunch of these 3 chemicals into a flask, that's not necessarily going to be at equilibrium. It's not like however much I start with is the same amount that I end with. They have to have this certain point where the right amounts of concentrations have been reached. And we'll talk about what that is in a minute. And so we can kind of watch this or plot it on a time course, meaning as time occurs, what happens. So this is a picture from your book. So if we take this and we start off at 0 seconds, this is a little past 15, a little past 30, and a little past 45. And we have this reaction. So we have H2, hydrogen, reacting with iodine, going to HI. And when we start off, they're starting us off with just reactants. For the record, that doesn't necessarily need to be true. We could have thrown in some product and some reactant. We could throw in a mixture of whatever we wanted. But for the sake of this graph, we're just starting with reactants. So we start off here. We have no HI, right? Because we started off by not adding any. And we watch what happens. So this is like starting that Avengers My Friends face off. We have some of the reactant, we don't have any product. And this forward reaction is going to take off and start creating some HI. And then over time, what we end up with is this graph where we get a bunch of HI, we get less of the reactants, and at some point it levels off. That point where it levels off is when equilibrium has been reached, because nothing's changing in the sense that the amounts aren't changing. Now, that doesn't mean that nothing's changing, right? For the individual molecules, things are changing. For the individual molecules, some of the hydrogen gets turned into HI, and some of the HI is getting turned into hydrogen and iodine. But when we look at it in bulk properties, when we look at the total concentrations, they aren't changing. Okay, so just to kind of review what we just talked about before moving on a bit. So we have a dynamic equilibrium when our forward and our reverse reactions are going the same speed, okay? And because of that, because they're both happening at the exact same pace, that means that the total concentrations aren't changing. So we can identify that on a graph when they level out. And you won't necessarily always have more products and reactants or more reactants and products. We need to talk about all that a little bit later once we know some more things. But we can at least say from this point on, we have a dynamic equilibrium because my amount of concentrations of my species are not changing. Now, okay, that's great, but how do we know what these concentrations are? If we have a graph, sure, we can just kind of look at it, but can we calculate that? And yeah, it turns out we can. We need to introduce a number for this. And we're going to call this the equilibrium constant. So the first equilibrium constant we're going to talk about is Kc. Now, throughout the quarter, we're going to have Kc. Very shortly, we're going to have Kp. Then we're going to have Ka and Kb and Ksp, Kd, and I think another one or two that I'm missing in there. They're all the same thing though. The little subscript just gives us very particular cases. Now one thing I want to point out that this is not the kinetic K, okay? So you had a K last quarter, you talked about being a rate constant. This is not that. This is a different K. But all of the equilibrium constants with some subscript are the same thing. So don't think of them as different things, it just talks about very specific cases. Okay, so what do we want to do with Kc? We want to be sure that we can write them. So right now we're just going to talk about them in terms of equations. Then we want to use data that we actually collect to figure out what the Kc is. So we can do experiments, we can do measurements, and we can use that to find this value. And this value becomes very useful for many, many calculations that we'll do throughout this chapter. Now, once we get Kc, we can use this number to tell us, well, are we going to have more products or are we going to have more reactants? Which one's favored? That's a useful thing to know. And we can use Kc to do that just by looking at it and comparing it to 1. And so we want to be able to do all three of those. Okay, so let's look at this a second. And I have this at a couple of different starting conditions. So this is a very similar graph to the one we just saw, except that we're changing starting conditions. The reason I want to do this is I want to show you something about the ratios at the end. So here we start out with no N2O, so we don't have any of what here is the reactant, and we have all NO2. This one's reversed. We start out with none of the NO2 and all N2O4. And then here we start out with some of each. So right now we just have a time course, and we're just kind of looking at it and seeing, well, what do we think could relate all of these numbers together? These don't all end up at exactly the same place. This is not a strict ratio-based system, meaning you can't just put products over reactants and be done. So there's a thought maybe, well, what if I just do a ratio? And we'll actually use that for some things, mostly in acid-base chemistry next chapter. However, for when we actually want to see, well, what's favored, products or reactants, we actually want to look at this, we need a different number. Just a ratio isn't going to quite work. And just quickly remembering, in each of these cases where that line is drawn is where equilibrium is reached, because that's where the point isn't changing. It's kind of a bit of review on a slightly different graph. So here's what we do instead. Since we can't do just a strict ratio for this particular purpose, because it's going to change. A ratio would change based on the starting conditions. We instead have a different formula. Again, this is the same for all your equilibrium constants, but in this case, we're talking about concentrations. That's what the C stands for, is concentration. So I have a very generic reaction here. AB goes to CD. The little letters in front of each one, those are your coefficients, right? Your coefficients. So your coefficients matter here. When you go to fill this into a Kc equation, you put the concentration, so these square brackets represent concentration. Whenever you see the square brackets, think concentration. You have products over reactants, and you raise them to the power of the coefficient. That's a really easy thing to forget when you're doing these. Put a kind of mental checklist of common mistakes in your head. Always check to make sure you raised it to the coefficient. Very easy to forget. Now let's do an example. So we have a real reaction. It was the one we were looking at earlier. N2O4 turns into two NO2s. So we put our products first. We have NO2 raised to the second power, or squared. Remembering that coefficient there. Divided by our concentration of N2O4. And that's just raised to the power of 1. And so we can leave it just as it is. We don't need to put the 1 there. If it helps you to always put the 1 there, you can, but you don't need to. Okay, let's do a few examples. So we'll do a couple of examples where all we're doing is writing the formula. And then we'll do one example where we're actually calculating it. To calculate it, no surprise, you just fill in the numbers. So once you get that Kc equation, if you have all the numbers you need to fill in, you just fill into it. So we'll do that example too. Again, I like working all of my examples on the document camera, so. That's what I will do. So first off, just writing the equilibrium constant. We'll start off with this one. We need to do products over reactants. So we'll write Kc. We'll put our NO here. Now, what do I need to remember to do? Square it. And then down here, we'll do that. We're talking about Kc here, so I wrote the Kc. We will also talk about Kp later on in a few minutes. We could have done that here as well, but we haven't learned that yet, so we're not doing that one yet. So now the next one. I have some things underlined on this one. For this one, we need to pay attention to the fact that we have solids here. Do solids really have a concentration? No. Nor do liquids. So we're not going to count solids or liquids in these equations, okay? We'll talk a little bit more about why later. We'll go into it a little bit more. For right now, we'll just kind of stick with because. So we never include solids or liquids. We include aqueous and we include gases. In this case, do I actually have a denominator then? Do I have any reactants that I'm going to include? No, I don't have any gas or aqueous species over here. So I come over here to my products. And I don't actually end up with a denominator. If you don't like that, if that bugs you, you can put a denominator of over 1, I guess. It just looks a little funny. Now let's do this one. Here we have all aqueous species, so all of them are going to be included. We do products. over reactants. We have our Kc. This one I actually included for a very specific reason. Once we get to acid-base chemistry, we're going to see that this one actually has a special name too. So we can call it Kc for right now. We're okay with that? Yeah.
What's the difference between aqueous and liquid?
So with our aqueous things, those are our ionic species that are dissolved into our liquid. So something like sodium chloride, where it's dissolved in as a plus charge and a minus charge. Something like this here, where we have this breaking up into the two, this would be in water. So aqueous is always something dissolved in water. Where our liquids, we'll see why when we have some diagrams and stuff, why that doesn't matter for these. Okay, now let's do an example where we actually calculate these things. As far as writing these go, you want that to be fast and automatic. You are going to have to write these for pretty much every single problem you do. So this should be a very quick, very automatic thing by the time you get going. All right. Pure phosgene gas, COCl2. I would not expect you to know what phosgene is, right? So we'll have a bunch of chemical names here that are named by kind of what we call them. Those are the sorts of names you don't need to know how to do. You need to know your ionic and molecular nomenclature, not all of these specific ones. So COCl2. I tell you how many moles was placed in a 1.5 liter container. And then I tell you it was heated to 800 degrees, and the pressure of CO was found to be 0.497 atm. Calculate the equilibrium constant Kp for the reaction below. So you need to calculate it for this reaction. And I give you this reaction. Again, not a reaction that I would expect you to know, unless I gave you some more information. When we go to do this, we can write a Kc for this equation, or a Kp for this equation. Actually, let's hold off on this one. We're going to come back to this one later. Okay. I got a little misplaced. All right. I mentioned this a little bit before when we looked at that one graph. But I want to mention again why we use Kc as opposed to just a ratio. We will actually end up using some ratios. There's something related to it later on. But let's look at this example. So this goes back to the very first example we did. And let's just look at some numbers. We're not going to calculate these right this second. They're going to be calculated for us. So this is from your book, but it's a really useful illustration here. So let's say we start off with these initial concentrations. At the end, we don't know how to calculate this yet, not a big deal, we'll get there. At the end, we have these three concentrations. So we can fill this into K. So let's talk about how you calculate K. You take your equilibrium conditions and you fill them into your equation. Okay? In the simplest form, that's all you have to do. We'll have some more complicated versions of that later on. So if you have your equilibrium conditions, you just fill it into your equation. And that's what they did here. This goes into your top. These two go into your bottom, and you get 50. All right? Let's do this 4 more times. Again, all of this is online. This is actually in your book too. So this is not the sort of thing that you want to spend a lot of time scribbling down. This is exactly the reason I give you the slides, is so you don't have to scribble all this down. Here, we have a different set of initial concentrations. And at the end, when we get our final concentrations, we can calculate a Kc with that. So we fill this in here, we fill in here, we fill in here. And look what happens. What do you notice about all these numbers, regardless of what your initial concentrations are? What do we come out with at the end? Same number. And that's why Kc, and eventually we'll get to Kp, that's why those are really useful. Is because we can take those and we can say, all right, we know this. We can use the numbers to back calculate, we can calculate them forward, we can do a lot of it with this because they're always the same as long as your temperature is the same. Okay. So we've gone through, we've defined Kc. We saw how they're calculated. We can't do a lot of complex calculations quite yet because we don't really have enough information to do it, but if we have our equilibrium calculations, we can see how to calculate it. Now let's talk about what the number itself actually means. So let's look at our generic Kc equation again, just super generic. For the record, this slide this is going to apply for every single K that we talk about. For every single K that we talk about, we're going to talk about it again. But keep in mind that it's really just the same thing in every different circumstance. So if Kc is significantly greater than 1, what does that mean about the concentrations of products over reactants? And if the Kc is significantly less than 1, what does that mean about the products over reactants? So let's look at 2 of these examples. I stole these from your book as well. So here we have an example, and they didn't even give you numbers, and that's great, because we're just going to say it's a large number. In other words, it's a lot bigger than 1. And here we have a different example, and in this case, it's a lot smaller than 1. What does this actually tell us about the reaction? Because we would like to be able to look at these numbers and know something without doing any calculations. The calculations for this section are relatively complex, and it's good to be able to know what's going to happen before you actually do them. If this is a large number, what's true about the top of this? Is that going to be small or big in compared to the bottom? It's going to be big. So that means we're going to have a lot of product or reactant? A lot of product. So when we go to look at this, we're going to have a lot more product than we would reactants. Now what about our small number? If we have a small number here, what does that mean about the top? Is it going to be small or big? Small. And so overall, are we going to favor our reactants or our products? Reactants. So by just looking at K, we can go through and we can say, all right, I know that if it's a lot bigger than 1, that I'm going to favor my products. I know that if it's a lot smaller than 1, I'm going to favor my reactants. Now what if it's pretty close to 1? What does that mean? We're relatively close to each other, right? That means that there's going to be a good amount of each. Okay, so quick review then on this section before moving on. We know that we have our K equation. We talk about it right now, we're talking about it in terms of Kc, but we want to keep in mind that it's actually in terms of, we can talk about the exact same sorts of things in terms of other units as well. So it's going to be products over reactants raised to the power of the coefficient. And we do that because that makes sure that regardless of what our starting condition is, we end up with the same number at the end of it. We're not going to end up with a different number just because our starting conditions are different. We can calculate the Kc just by filling in our equilibrium conditions. That'll get a little more complicated as we move on, but we at least got to see it done once. If Kc is way greater than 1, then our products are favored. If Kc is way less than 1, then our reactants are favored. If it's about 1, then they're about the same. Keep in mind that this is going to be true, and I said the last 2, but I mean really in a lot of ways all of them, are going to be true for all of the equilibrium constants we cover. Don't think of each new equilibrium constant I introduced to you guys as this is new thing that you have to learn all over. It's really the same idea over and over and over and over again. So speaking of, let's do pretty much the exact same thing for Kp. The P here stands for pressure, just like the C stood for concentration. So we're going to quite literally do everything pretty much the same idea. We're going to say, okay, well, given an equilibrium, how do we write Kp? We want to use data to calculate the equilibrium constant. Again, we're keeping this relatively simple for right now. We'll get more complex as we go along. We want now to find the relationship between Kc and Kp. Because Kc and Kp aren't quite the same thing. One's in terms of concentration, one is in terms of pressure. They're actually different units describing the exact same thing. So we would like a way to interconvert between the two. This is where your ideal gas laws come in. So if you need to brush up on your ideal gas laws, just race back and do a little bit of brushing up on it. Normally you guys kind of like that chapter, so it shouldn't be too bad to brush up on. Okay, so no surprise. Let's say these are all gases. We take and we can say, okay, well, what's our pressure of C? Raise that to our power of our coefficient. What's our pressure of D? Raise that to our coefficient. Pressure of A, pressure of B, raised to our coefficient. I'm not going to go through explaining why we like having this number. It's the exact same reason as before. It keeps all of the numbers the same regardless of starting conditions. So we can do the exact same thing for this reaction. So we defined it in terms of Kc last time. Because it's a gas, we can do that. We can say what's the concentration of a gas. It almost makes more sense to do with pressure though, right? So now we do the exact same thing. We say, well, what's our pressure of our products raised to our coefficient divided by our reactants raised to our coefficient, which in this case is raised to a power of 1. If you want to write that in, go for it. If you don't worry about it. You really don't need it. Now, it would be really nice to be able to relate these two together. So let's first do a couple examples just using this, and then we'll talk about how to go back and forth. Can we go back to the document camera? Let's write each of these in terms of Kp now, if we can. Some we can, some we can't. So let's look at this one first. Didn't go, thank you. All right, so let's do this one because we can, right? All gases. So we could also write Kp. Not too much changes here. We just basically change the unit. Okay. For this one, we also have a bunch of gases, so we can write Kp for this. Do you think for Kp you add aqueous species in? No, aqueous species can't have a pressure. For the same reason as here that we didn't include solids, we don't include solids here. We'll go more into detail about that later. And, whoops, erase this a sec. So we have our pressure, CO2, times by our pressure of H2O. And we're done. For the last one, can I write a Kp? Doesn't make any sense to write a Kp for that, right? Because aqueous species can't have a pressure. So the last one we can't do much with. Okay, now let's do this one. Phosgene gas. So we already read it to you. But now we can actually do the Kp. We need to figure out our equilibrium concentrations for this. And to do this, we're going to kind of have a standard mode of doing this, where we write in something called an ice chart. Just quick show of hands for me. How many have heard of an ice chart before? Or an ICE chart? Okay. Now, all that is basically a mental note-keeping device to say, what are all of my conditions at all of my different times, and keeping track of things. You'll get where for some of these easier problems you don't need to use it. I still like to use it even for the easier problems when I'm describing things to you. So I'll use it kind of regardless. So what we do is we say there's going to be a bunch of initial conditions. And then time is going to take place and they're going to react. And when they react, things are going to change. And after all of those changes take place, we're going to reach an equilibrium. This is where it becomes very Sudoku puzzle-y, where you fill in what you know, and then each time you learn something, each time you fill something into the table, you can fill in something else because of it, and you can fill in something else, and eventually you get what you want. Okay, that's the most generic way of describing the problem-solving techniques for the next 3 chapters. We know some things right away about this. Pure phosgene gas, this, was placed into a 1.5 liter container. Was any mention made of either of these gases? No. So how much did I start out with? If we don't put any of it into the container, how much do I start off with? 0. Now I do start off with some COCl2, right? This, I do need to figure out, okay, well, how much of this did I put in? I have this mole value. Should I just fill that in? No, because what am I trying to find? Kp. So I need to figure out a way to get this in terms of a pressure. So I have moles, I have volume, I have temperature, and I need pressure. What is that starting to sound like? An ideal gas law. We have PV equals nRT. We solve for P. We fill in our values. I'm a little short on room, so I'm going to kind of nix units. Now, in this case, I already have my temperature in the right units. If I had it in Celsius, what would I have to do? You would have to turn everything to Kelvin, right? It's always got to be in Kelvin. So don't forget that, because it was a while ago that that was an issue. And we get our final pressure. Well, let me rephrase. We get our pressure. We can take this, and we can now fill that into here. In your ice charts, you want everything that you fill in to be the same units, okay? So generally, when I fill into ice charts, I don't actually put my unit on every single number because it makes it a little bit messy, a little bit hard to read, and it's not super necessary. But maybe you want to write something out here saying, oh, by the way, this is an ATM. This is less important when we're doing just Kc or Kp. It becomes more important when we get into some complex titrations, acid-base, things of that sort. Okay. So now, let's see what else we have / haven't used. So we've used this, we've used this, we've used this. And now I say the pressure of CO was heated to 800 degrees. The pressure of CO was found to be 0.497 atm. So we know something. Well, we know lots of things, but we know something related to this problem. We know this. So we fill this in here. We know that after everything has reached equilibrium, that we have that value. So now we can go back through and calculate the rest of these. Because if this went from 0 to 0.497, how much did it change by? Yeah, we added 0.497 to it. So this number gave us that number, right? Now let's look at our coefficients here. 1 to 1 to 1. It's a balanced reaction, 1 to 1 to 1. If this changed by 0.497, how much did this have to change by? So that gives us this, which also says how much did this have to change by? 0.497. Did I add 0.497? if I added more of this, where did it come from? So what do I have to do here? Subtract. Okay. Great, now I have all my changes. So now I can use this to also say, well, I started with 0 and then I added 0.497. So perfect. And I started with 1.31 here and I subtracted off 0.497. So I can get my number there. Now, all of that was to get my equilibrium concentrations. We see how this starts getting more complicated. We could have done this for Kc as well, but build a little bit at a time. So now all of that got us our equilibrium values. Why did I want my equilibrium values again? Let's keep track of what we're trying to do here. I want Kp, right? And we know that our values for Kp are always our equilibrium values. If we're not using equilibrium values, it's not K. We actually have a special name for that we'll talk about later. Now everything becomes the same as before. We fill in. So let's go ahead and write our equation first, just because we haven't had a huge amount of practice on that. So we have our products over reactants. I'm going to change this to parentheses just so that technically the square brackets always mean concentration. So changing it to parentheses keeps that notation from being there. Not a big deal, but we write this. So we have our products, we have our reactants, and now we just fill everything in. If you're looking at this and saying, why couldn't I write 0.497 squared? You could. I'm not doing it purely so that you can see that I'm just filling this number into both of here. But you could do that if you wanted, that's fine. And we type that into our calculator and we get our number. Okay. Where most of the complications come in on doing these problems is trying to get to these equilibrium values. So I talk about not memorizing how to do all of these problems individually. This is our first chance to see what I mean here. Most of our problems in this class are going to be fill into an ice chart, fill into K something. Leave it as that, K something. Now, how you go about filling into the ice chart is going to change based on exactly what conditions they give you. But all of it is taking all of the information they give you and filling it into the right spots. Once you get all the information they've given you filled into the right spots, it's saying, okay, well now that I have this all filled in, what other spots can I fill in? And once I get those filled in, what other spots can I fill in? And just walking through that until you get to whatever conditions you need. Typically, that's your equilibrium conditions. And then you fill into whichever K you're talking about. In this case, Kp. Give a second to copy that down. Let me see a few people still writing. Now, if we're given the information to calculate Kc, it would be really, really nice if we could just get Kp right from there. Or if we're given the information to calculate Kp, it would be really, really nice if we can just get Kc right from that. And theoretically, based on how we did this one, you could always do that by going back and taking all your pressures, using the ideal gas law to convert into your concentrations or vice versa, and constantly going back and forth and then redoing the entire problem. Who thinks that sounds like fun? Yeah, I think it kind of sounds like fun, but it's also inefficient. And so as fun as it is as an exercise, and I see you all totally agreed with me and the one other person, we don't really want to do that when it comes to trying to be efficient and quick. And so what we're going to do instead is we're going to use this relation. But I want you to know where this relation comes from, because if we just throw a bunch of random equations at you, that makes life kind of boring. So this is the equation that we can use to go back and forth. If you know what Kc is, you can find Kp. Let's talk about the other numbers here. What is this R? Ideal gas constant. Now, we've been talking about the ideal gas law. We haven't been talking about any sorts of energies. So which R do you think we're going to use here? 0.0821, the one with liters, atmospheres, moles, and kelvins in it, right? Not the energy-related one. Okay. T, take a guess. What is T? Temperature. What unit? Kelvin. So now N. What does N normally stand for? Moles. Delta means, so this is between your products and your reactants, okay? It's a change in moles of, do we think probably gas, aqueous, both? I think. It's a gas here, okay? All we really care about is the moles of gas when we're doing this. It's the change in moles of gas from your products to your reactants. And this does not mean in terms of exact going in and looking at the data numbers of moles. You use your coefficients for this, okay? So if we look back on this one, what's your change in moles between here and here? It's a change of 1, right? Because you have 2 moles on this side, 1 mole on that side. 2 minus 1 is 1. That's what we mean by change in moles here. So a nice little formula. Let's figure out where it comes from. And we'll use it a little bit. So I have kind of 2 parallel tracks here. We are going to start doing some derivations in this class. I think maybe if you had me for 1A, I might have thrown at max 1 at you. We're going to do a few more in this class, because now we have enough pieces that we can see where they kind of come from. We won't do too many because it gets a little rough to watch. We have our PV equals nRT. We got that from 1A and 1B. This is my generic reaction. I just picked a very simple generic reaction. Simpler is better for this sort of thing. Now, we can write Kp, right? So let's write Kp. Done this? Now, that's our 1 parallel track. Let's come over here. I can write this in terms of pressure, yeah? I can take and go P equals nRT over V. Now, if we're trying to relate Kc and Kp, we need to find a concentration in here. And we can do that because we have moles and we have volume. We have molarity hidden in here. So let's just rearrange. And we're not even really rearranging, we're just kind of exaggerating something here. We're saying that this is actually moles over liter. That's concentration. Now I can take that and I can fill that into here. Okay? So I'm taking this whole equation and I'm just popping it into my Kp equation. Why? Well, it's going to let us pull out our Kc. So we do that. Remember, this is our goal. This is what we're trying to get to, because we need to keep that in mind when we do derivations. So we've taken this. We've said, oh, hey, look, we have a concentration in here. That could be useful. We fill this whole thing into pressure, because this is pressure, so we can fill the whole thing into pressure. And now we have this set up. Let's rearrange it a little bit, because we've already said that N over V is equal to concentration. So why would we leave this as N over B or N over V when we're trying to get to a concentration anyways? So we'll just say that whole thing is our concentration of B, and this whole thing is our concentration of A. And now we factor out the RT. So we factor out the RT, and we would have RT to B over RT to A. If you need that in between step, you can write that. RT over B over RT over A. Now we use our rules of exponents. And that's where that delta N comes in, right? Because we know our exponents on our product side and our reactant side theoretically. We know that this is some number. We know that this is some number. And that the change in moles between here and here, that's our B minus our A. That's our exponent rules, right? If you're trying to divide that and you have the exact same thing, you subtract the exponents. Think way back 7th grade, 8th grade, something like that, when we learned exponent rules. It's dividing, you do subtraction. That's where our delta N comes in. And that's why it's products moles subtract reactants moles, because it's coming from right here. Product moles minus reactant moles for our RT. Okay. The level of which, because it's going to come up at some point, someone's going to ask about the level of which this sort of thing is required for replication. I would not require you to replicate this whole thing. So don't sit at home and memorize how to do it. This is something that you could theoretically memorize, so I'm not big on asking questions about it. I would more ask a very conceptual question. You know, explain to me why Kc and Kp are related. Something of that sort. So keep that in mind. I'm never going to ask you to replicate a whole derivation. I care more about the idea that you got the concept down than that you can redo it. If you go to PChem, you can learn to do all the derivations. Okay, let's do a couple more examples here. Notice I didn't give you a reaction here. And maybe you're saying, well, I can go back in my notes and find the reaction for this. This is true. But keep in mind, this is why knowing your nomenclature is important, because for things that just involve normal ionic or molecular nomenclature, I don't need to give you the whole reaction in terms of chemicals. I can just tell you the names of it, like I did here. So find Kp for the decomposition of phosphorus pentachloride. So phosphorus pentachloride. So how many chlorides? The decomposition of that into phosphorus trichloride. How many chlorides on that one? And chlorine gas. Is that chlorine gas? No. What do we have to do? Don't forget about your diatomics, right? So oxygen, nitrogen, fluorine, chlorine, bromine, iodine, and hydrogen. We have this. All of these are gases. I should have told you that phosphorus pentachloride was a gas in the problem as well. I would tell you that. Given that the equilibrium partial pressures, and I tell you the equilibrium partial pressures, and then I say find its Kc. Do we need to make an ice chart for this one? What do I give you already? I give you the equilibrium pressures. Don't make an ice chart if I already give you everything you need to do it. I guess you could, but you really just need to write your Kp. And again, different parentheses. I'm being a little picky in my notes about not messing up the parentheses for you guys. In reality, I'm not particularly picky about that. You should keep in mind that the square brackets do mean something specific, but it's not the end of the world if you mess it up. I have no coefficients here, so I'm all set. It's good to think about that each time you do it, though, just to make sure that you're remembering that. Now I fill in my values. So I have my chlorine. I have my PCl3. So we're just careful to fill in all the values as they were given. And there's something that nobody has yet called me out on. Yeah, units. I've not put units on any of these Ks. Is that okay, or have I just been, messing you up for the last hour? It is correct. Equilibrium constants don't actually have units. When we fill them into the equation, we're doing something behind the scenes that we're not really going to go too far into, where we're basically doing away with the units. So we'll go more into that later, but for now. So now to finish this problem up, we have this equation. And we're going to use this equation to find Kc. We have this. We fill in all of our values. Notice when I fill in, you should really use more sig figs, right? We have to watch out for our units on temperature because I gave it to you in Celsius. What is our delta N here? How many moles of gas do we have on this side? And how many on this side? So what is our delta N? 1. I'm going to go ahead and just put that little 1 there just to drive that point home. You obviously don't have to. And we end up with that. Also no units. Okay, and we will finish up the rest of this part of the thing next class.